Have you ever rubbed a balloon on your hair and watched it stick to the wall? That's the magic of electrostatic forces at play. In the vast universe, forces govern the interactions of everything around us. They are the invisible hands that push or pull objects, dictating their motion and behavior. Among these forces, there exists a fascinating phenomenon known as electrostatic force. This force arises from the fundamental property of matter called electric charge. In simple terms, a force is a push or pull that can change the state of motion of an object. When a force acts on an object, it can cause the object to start moving, stop moving, or change direction. There are many different types of forces in the universe, including gravity, friction, and magnetism. Electrostatic force is one of these fundamental forces. Electrostatic force, also known as static electricity, is the force that exists between electrically charged particles or objects. It's the force that makes your hair stand on end when you rub a balloon on it, or the spark you feel when you touch a doorknob on a dry day. This fascinating force arises from the presence of electric charges, which can be either positive or negative. Let's delve into the world of electric charges. Just like magnets have north and south poles, matter possesses two types of electric charges, positive and negative. These charges are intrinsic properties of the particles that make up atoms, the building blocks of all matter. The basic unit of matter is the atom, and every atom consists of even smaller particles, protons, neutrons, and electrons. Protons located in the atom's nucleus carry a positive charge, while electrons orbiting the nucleus possess a negative charge. Neutrons, as their name suggests, are electrically neutral, carrying no charge. Now, how do we detect these invisible forces and charges? Scientists have developed ingenious instruments, one of them being the electroscope. An electroscope is a simple device used to detect the presence of electric charges. A simple electroscope consists of a metal sphere connected to a metal rod. At the bottom of the rod, two thin metal leaves are suspended. When an object with an electric charge is brought near the sphere, the leaves will either repel or attract each other, indicating the presence and type of charge. Charging by conduction is one way to charge an object. In this method, a charged object is brought into contact with a neutral object. The charges from the charged object transfer to the neutral object, giving it the same charge as the charging object. For example, if a negatively charged rod touches a neutral metal sphere, electrons from the rod will transfer to the sphere, making it negatively charged. Another method is charging by induction. In this method, a charged object is brought near but not touched to a neutral object. The presence of the charged object causes a separation of charges within the neutral object. For example, if a negatively charged rod is brought near a neutral metal sphere, the electrons in the sphere will be repelled and move away from the rod, leaving the side of the sphere closest to the rod with a positive charge. Section 4. Coulomb's law and the strength of electrostatic forces. The strength of the electrostatic force is not arbitrary, it is meticulously governed by a fundamental law of physics known as Coulomb's law. This law, named after the French physicist Charles-Augustin de Coulomb, quantifies the force between two point charges. Coulomb's law states that the force between 2 point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. This means that the force gets stronger as the charges get larger and weaker as the charges get farther apart. Mathematically, Coulomb's law is expressed as F equals K times the product of Q1 and Q2 divided by R squared, where F represents the electrostatic force between the charges, K is Coulomb's constant, Q1 and Q2 are the magnitudes of the 2 point charges, and R is the distance between the charges. Section 5. Applications and significance of electrostatic forces. Electrostatic forces might seem like a hidden phenomenon, but their applications are far-reaching and impactful in our daily lives. From the mundane to the cutting edge, these forces play a critical role in various technologies and natural phenomena. One prominent application is in photocopying machines. These machines use electrostatic forces to attract toner particles to the paper, creating copies of documents. In the realm of painting, electrostatic spray painting utilizes charged paint particles that are attracted to the grounded object being painted, resulting in an even coat and reduced paint waste. Electrostatic forces are also essential in understanding the behavior of atoms and molecules. The bonding between atoms and molecules is largely due to electrostatic interactions between electrons and nuclei. Furthermore, many biological processes such as the transmission of nerve impulses rely on the interplay of electrostatic forces. Understanding electrostatic forces is crucial for comprehending the intricate workings of our universe. From the simple act of a balloon clinging to a wall to the development of advanced technologies, these forces shape our world in profound ways. As we delve deeper into the mysteries of the universe, a firm grasp of electrostatic forces will undoubtedly pave the way for groundbreaking discoveries and innovations.